High above, two silent sentinels hang in the night sky. One is Oumuamua, an interstellar traveler spotted in October 2017 by the Pan-STARRS-1 telescope in Hawaii. Its trajectory and speed, 95,000 kilometers per hour relative to the Sun, marked it as the first observed object from beyond our solar system. So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means, and if you want to help this message. Reach others who still wonder, share it, on X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. The other is C20F3 Neowise, a comet from the Oort cloud discovered in March 2020 by the Neowise Space Telescope. Despite differing origins, these objects share striking similarities, their movements echoing each other like cosmic counterparts. Oumuamua, whose name means scout or messenger from afar in Hawaiian, has a unique cigar-like shape and a chaotic tumbling motion. Its mysterious acceleration deviating from expected gravitational paths has sparked debate, with some attributing it to outgassing, despite no visible comet-like tail. Neowise, a long-period comet, exhibited sudden brightness outbursts near its perihelion in July 2020, its tail displaying intricate structures and unusual ionization patterns that defy explanation. The simultaneous presence of Oumuamua and Neowise offers a unique comparative lens, yet their shared characteristics remain unexplained. Both exhibited unusual brightness fluctuations and accelerations, deepening the mystery. Some researchers cautiously suggest these objects could be products of advanced civilizations, citing Oumuamua's trajectory and shape as consistent with a solar sail. This controversial hypothesis has gained traction due to the lack of satisfactory natural explanations. If these objects are indeed of intelligent design, their presence could signify cosmic surveillance. Their synchronized appearances and defiance of known astrophysical principles might be deliberate rather than coincidental. This speculation raises profound questions about humanity's role in the cosmos and the potential for contact with extraterrestrial intelligence. As Oumuamua fades from view and Neowise continues its journey back to the Oort cloud, astronomers are left to ponder their mysteries, challenging our understanding of the universe and offering a glimpse into the unknown. Part 1. Unlikely Sentinels. What if the universe were watching us? The cosmos, vast and indifferent, suddenly feels a little closer, a little more personal. Two comets, one interstellar and one local, now sit on opposite sides of Earth, their trajectories and appearances mirroring each other in ways that defy simple explanation. This isn't just a tale of celestial wanderers, it's a story of synchronization of two disparate bodies moving in concert, as if guided by an unseen hand. The odds of such a scenario are astronomical, yet here we are, witnessing a cosmic ballet that seems almost choreographed. 3 Atlas, the interstellar interloper, screams toward the Sun on a hyperbolic orbit, its velocity marking it as a visitor from beyond our solar system. Its journey has been epic, traversing the unfathomable distances between stars. Estimated to have begun its voyage millions, if not billions, of years ago. 3 Atlas carries with it the stories of distant suns and alien worlds. Its composition is exotic, its surface a time capsule of cosmic history, etched with the radiation and dust of eons past. Spectroscopic analysis reveals traces of elements rarely seen in our solar system, hinting at the vast differences in stellar environments across the cosmos. R2 SWAN, supposedly a long-period comet from the Oort cloud, was expected to behave predictably, boring even. Yet, as it approaches the inner solar system, it has begun to reveal its own surprises. The Oort cloud, a theoretical spherical shell of icy bodies far beyond Pluto, is thought to be a remnant of the solar system's formation. R2 SWAN, therefore, is a local, a product of our own celestial neighbourhood. Its journey, while not as grand as 3 atlases, is no less profound. It has spent most of its existence in the deep freeze of the outer solar system, only now venturing into the warmth of the sun's embrace. Recent observations have shown that R2 SWAN's surface is pockmarked with ancient craters, evidence of collisions that occurred during its long sojourn in the Oort cloud. Both comets, despite their differing origins, now display bizarre tail structures and plasma jets that challenge our understanding of comet behavior. Their tails, stretching out like gossamer veils, shimmer in the solar wind, painting the skies with their ethereal glow. The plasma jets, bursts of ionized gas propelled by the sun's heat, dance and flicker like solar flares, their intricate patterns a puzzle for scientists to decipher. These jets have been observed to change direction rapidly, suggesting that the comets are subject to fluctuating magnetic fields or other dynamic forces. Observation: the tails of both comets defy convention, with portions facing toward the sun, contradicting the standard model of solar radiation pressure pushing dust away in the opposite direction. This phenomenon, known as anomalous tail directionality, has been observed in only a handful of comets, making the simultaneous occurrence in 3 Atlas and R2 SWAN all the more remarkable. The plasma jets, too, exhibit unusual behavior, their velocities and directions suggesting complex magnetic interactions at play. In some instances, the jets have been seen to spiral around the comet's nuclei, creating stunning visual displays that have captivated astronomers and amateur skywatchers alike. Interpretation: this could be a result of complex outgassing dynamics or rotational effects, but the fact that both comets exhibit this behavior simultaneously raises questions. The standard model of comet behavior, based on decades of observation and study, struggles to account for these. New findings. Some researchers propose that the comet's unusual tail structures and plasma jets could be due to previously unconsidered factors, such as the influence of the sun's magnetic field or the presence of unseen companion bodies. Recent simulations have shown that the gravitational influence of a nearby but undetected planetary body could, in theory, alter the trajectories and behaviors of both comets in ways that align with current observations. Speculation: could an external force or shared history explain their mimicry? Or is this a cosmic coincidence, a convergence of independent processes that just happen to produce similar results? The idea of an external force acting on the comets is tantalizing, conjuring images of mysterious cosmic entities or undiscovered physical laws. Alternatively, the comets' shared history could hint at a past interaction, perhaps a close encounter that altered their trajectories and behavior. Some researchers have even floated the possibility that the comets could be fragments of a larger body that broke apart during a catastrophic event millions of years ago. However, the notion of a cosmic coincidence cannot be dismissed, as the universe is vast and full of surprises. The comet's approach has sparked a flurry of activity among astronomers, their telescopes trained on the celestial visitors. Ground-based observatories from the towering Mauna Kea in Hawaii to the remote Atacama Desert in Chile have been monitoring the comet's progress. Space-based telescopes such as the Hubble and the recently launched James Webb Space Telescope have also joined the effort, their advanced optics providing unprecedented views of the comet's structures and compositions. The James Webb Space Telescope, with its infrared capabilities, has been particularly valuable in studying the thermal properties of the comets, revealing hotspots on their surfaces that suggest areas of intense outgassing or subsurface activity. As the comets approach their closest points to the Sun, the stakes are high. The period of perihelion, when the comets are nearest to the Sun, is a critical time. The intense heat and solar radiation can trigger dramatic changes in the comet's behavior, from increased outgassing to potential breakup. We are being flanked by objects that should have nothing in common, yet their resemblance is undeniable. The question is no longer just about comet tails or plasma physics. It's about position and timing. Some models suggest that the comet's synchronized behavior could be a result of gravitational perturbations caused by the alignment of the planets in our solar system, a rare event that occurs only once every few thousand years. The comets synchronized. Dance has not gone unnoticed by the public. Social media platforms are abuzz with theories and speculations ranging from scientific curiosity to wild conspiracies. Hashtags like Sark Comet Twins and Cosmic Coincidence have trended worldwide, reflecting the global fascination with this celestial spectacle. Amateur astronomers, too, have joined the fray, their backyard telescopes capturing stunning images of the comet's tails and plasma jets. One, particularly striking image, taken by an amateur astronomer in Australia, shows the tails of both comets appearing to intersect in the night sky, creating a luminous X-shaped pattern that has been dubbed the Cosmic Cross. But beyond the public's fascination lies a deeper question. What does it mean the Earth is caught between these two enigmatic objects, and why do they seem to be performing the same cosmic dance? The alignment of the comets, they're mirrored. Trajectories and synchronized behavior seem almost too perfect, too orchestrated. It's as if the universe itself is putting on a show, a grand spectacle for the inhabitants of a tiny blue planet. Some cultures have even begun to interpret the comet's appearance as a sign or omen, incorporating them into religious and spiritual narratives. In Japan, for instance, the comets have been nicknamed Ryusei no Futago, or twin dragon stars, and are seen as symbols of balance and harmony. The scientific community, ever cautious, remains divided. Some researchers argue that the comet's behavior is merely a coincidence, a quirk of celestial mechanics and cometary physics. Others, however, are not so sure. They point to the unlikelihood of such a coincidence, the precise alignment and synchronization of the comet's trajectories and behaviors. Could there be more to this cosmic dance than meets the eye? Some have even suggested that the comets could be part of a larger, undiscovered cometary family, a group of objects that share similar orbits and characteristics due to a common origin. In the quiet halls of academic institutions and research labs, whispers of extraordinary theories have begun to circulate. Could the comets be remnants of a past event, a cosmic catastrophe that sent them hurtling through space? Could they be under the influence of an as-yet undetected celestial body, a rogue planet or a distant star? Or perhaps most intriguingly, could they be artifacts, not of nature, but of intelligence? The idea that the comets could be of extraterrestrial origin, either natural or artificial, has gained traction among some fringe scientists who point to the unusual composition and behavior of 3 Atlas as evidence of an otherworldly provenance. The idea of intelligent design behind. The comet's behavior is a controversial one, a topic that skirts the edges of mainstream science. Yet, it is a possibility that some researchers are reluctant to dismiss entirely. After all, the universe is full of surprises, and the line between the natural and the artificial can sometimes be blurred. As the comets continue their dance, their true nature remains a mystery, a cosmic enigma that continues to captivate and confound. In the meantime, scientists and amateur astronomers alike will keep their eyes on the skies, watching and waiting for whatever revelations the comets may bring as they journey through our solar system. Known: 2 comets, 1 interstellar, 3 Atlas, and 1 from the Oort cloud, R2 SWAN, exhibit strikingly similar morphological features. Their tails defy conventional explanation, with portions facing toward the sun, and their plasma jets display unusual velocities and directions. The comets' synchronized behavior and mirrored trajectories have sparked global fascination and scientific debate. Recent spectroscopic analysis has revealed the presence of complex organic molecules on both comets, raising questions about their potential role in the distribution of life-building materials throughout the cosmos. Unknown. Whether this resemblance is coincidental or indicative of a deeper connection. The true nature of the comet's behavior remains a mystery, with theories ranging from natural phenomena to intelligent design. The comet's perihelion approach promises to reveal more about their behavior and potential origins, but for now, their cosmic dance continues to captivate and confound. Some researchers have proposed coordinated observations across multiple wavelengths, from radio to X-ray, to better understand the comet's interactions with the solar wind and magnetic field. Part 2. Orbital choreography. What if their paths were not random? The vastness of space is not merely a backdrop for celestial objects, but a stage for an intricate dance of gravity, momentum, and time. Every object in the solar system, from the smallest asteroid to the largest gas giant, moves in response to the invisible forces that govern the cosmos. Yet, among the countless bodies that traverse the void, 2 stand out: 3 Atlas and R2 SWAN, their orbital mechanics seemingly disparate, hint at stories that challenge our understanding of celestial motion. The orbital mechanics of 3 Atlas and R2 SWAN tell 2 very different stories. 3 Atlas, with its hyperbolic trajectory, is an interstellar wanderer, its velocity too high to be bound by the sun's gravity. Travelling at an astonishing 57 kilometers per second relative to the sun, it defies the gravitational constraints of our solar system. Its path, a wide, open curve, suggests a journey that began far beyond the reach of our star's influence. R2 SWAN, on the other hand, follows an extremely elongated elliptical orbit, taking it from the inner solar system to the distant Oort cloud and back. This orbit, with a period of roughly 1,200 years, is a testament to the sun's enduring gravitational pull, even at the farthest reaches of its domain. Their paths intersect Earth's position along the ecliptic plane, but they approach from vastly different directions, like 2 travellers meeting briefly before continuing on their separate ways. Observation. 3 Atlas entered the solar system from a direction that does not align with any nearby stellar system, suggesting it has been travelling through interstellar space for thousands, if not millions of years. Its trajectory, when traced backward, points toward a region of space devoid of stars within a reasonable distance. This isolation in its origin adds to the mystery of its journey. The comet's composition, rich in heavy elements like nickel and iron, hints at a birthplace far removed from the pristine conditions of the early solar system. Interpretation. The comet's velocity relative to the Sun, dozens of kilometers per second, is far greater than anything born in our system could achieve without a massive gravitational assist. Such speeds are typically the result of close encounters with massive objects, like stars or black holes, which can slingshot smaller bodies into interstellar space. Yet, no such encounter has been observed in the recent history of 3 Atlas, leaving its origin and propulsion a puzzle. The absence of a clear gravitational perturbation raises questions about the forces that shaped its trajectory. Speculation. Could an undetected gravitational perturbation or an exotic propulsion mechanism explain such a trajectory? Some theories propose the existence of undiscovered celestial bodies, such as the hypothetical Planet 9, whose gravitational influence could alter the paths of smaller objects. Others suggest that 3 Atlas might be a fragment of a larger interstellar object, ejected into space by an unknown event. More provocatively, some researchers have entertained the possibility of artificial propulsion, though no evidence supports this claim. R2 SWAN's orbit, while bound to the Sun, is so elongated that it takes centuries or millennia to complete a single loop. Its perihelion, closest approach to the Sun, brings it to about half the distance between Earth and the Sun, close enough to heat up significantly and produce the coma and tail we observe. This proximity to the Sun transforms the comet, releasing gases and dust that create a spectacular display visible from Earth. At its aphelion, farthest point from the Sun, R2 SWAN ventures into the Oort cloud, a spherical shell of icy bodies that marks the outer boundary of the solar system. This region, untouched by the Sun's warmth, preserves the primordial material from which the solar system formed. The contrast between 3 Atlas and R2 SWAN extends beyond their orbits. 3 Atlas, with its interstellar origin, carries the imprint of distant stars. Its composition, altered by cosmic rays and interstellar dust. Its surface, likely scarred by micrometeoroid impacts and eroded by the relentless bombardment of high-energy particles, tells a story of survival in the harshest environment imaginable. R2 SWAN, by contrast, bears the signature of the solar system's birth, its icy core a time capsule of the early solar nebula. Its repeated journeys through the inner solar system have left their mark, with layers of dust and ice deposited over millennia. Observation. The orbits of 3 Atlas and R2 SWAN intersect Earth's path at intervals that defy simple explanation. While the solar system is filled with objects whose paths cross Earth's orbit, the timing and alignment of these 2 comets are unusually precise. Their approaches, separated by decades, have drawn the attention of astronomers and fueled speculation about their significance. The fact that both comets are visible from Earth during their closest approaches adds to the intrigue, as if nature itself has arranged this celestial spectacle for our observation. Interpretation. The intersection of their orbits with Earth's position could be a coincidence, a result of the complex interplay of gravitational forces in the solar system. However, the rarity of such alignments raises questions about whether an external factor might be at play. Some researchers have proposed that the gravitational influence of a distant, undetected planet could subtly alter the paths of comets, nudging them into alignment with Earth. Others suggest that the comets' orbits may have been shaped by past interactions with other celestial bodies, such as Jupiter or Saturn, whose massive gravitational fields can deflect smaller objects. Speculation: could the paths of 3 Atlas and R2 SWAN be influenced by something beyond our current understanding of celestial mechanics? Theories about the existence of dark matter and dark energy, which permeate the universe but remain invisible to our instruments, have led some to wonder if these mysterious forces could affect the orbits of celestial bodies. Others have speculated about the possibility of advanced civilizations manipulating the trajectories of comets for purposes we cannot yet fathom, while such ideas remain purely hypothetical. They underscore the depth of our ignorance about the forces that shape the cosmos. The study of 3 Atlas and R2 SWAN has sparked a renewed interest in the dynamics of celestial bodies. Astronomers have turned their telescopes toward the heavens, seeking clues in the motions of comets, asteroids, and other small bodies. Their observations have revealed a solar system teeming with activity, where gravitational interactions create a constant dance of objects. The orbits of these bodies, once thought to be fixed and predictable, are now seen as fluid and dynamic, shaped by forces both seen and unseen. Observation: recent observations of 3 Atlas and R2 SWAN have uncovered subtle deviations in their expected trajectories. These deviations, though small, are significant enough to warrant further investigation. They hint at the presence of unaccounted forces acting on the comets, forces that could challenge our understanding of orbital mechanics. The precise nature of these deviations remains unclear, but they have sparked a flurry of research and debate within the scientific community. Interpretation: the deviations in the comet's orbits could be the result of gravitational perturbations from known or unknown celestial bodies. Alternatively, they could be caused by non-gravitational forces, such as the release of gases from the comet's surfaces as they approach the Sun. This process, known as outgassing, can create a slight thrust that alters the comet's trajectory. However, the scale of the observed deviations suggests that something more than outgassing may be at work. Speculation: could the deviations in the comet's orbits be evidence of new physics at play? Some researchers have proposed that the comet's trajectories might be influenced by exotic forms of matter or energy, such as dark matter or dark energy. Others have suggested that the comets could be interacting with unseen magnetic fields or gravitational waves, ripples in space-time caused by violent cosmic events. While these ideas remain speculative, they highlight the potential for new discoveries in the study of orbital mechanics. Known: 3 Atlas and R2 SWAN have radically different orbital histories and energies. Their paths intersect Earth's orbit in ways that defy simple explanation, and recent observations have revealed subtle deviations in their expected trajectories. These deviations hint at the presence of unaccounted forces acting on the comets, forces that could challenge our understanding of orbital mechanics. Unknown: whether their current positions relative to Earth are purely coincidental or influenced by an external factor. The precise nature of the deviations in their orbits remains unclear, as does the question of whether these deviations are the result of known or unknown forces. The possibility of new physics at play, such as the influence of dark matter or dark energy, remains purely speculative but warrants further investigation. The study of 3 Atlas and R2 SWAN continues to push the boundaries of our understanding of the cosmos, revealing a universe filled with mystery and wonder. Part 3. The Morphology Problem. What if their similarities are more than skin deep? The more we scrutinize the images of 3 Atlas and R2 SWAN, the more their enigmatic behaviors challenge our understanding of cometary dynamics. These aren't just distant smudges of light. They are worlds unto themselves, each with a distinct personality shaped by their composition and history. The images of 3 Atlas and R2 SWAN reveal extended comas, clouds of gas and dust surrounding their nuclei, and tail structures that defy textbook explanations. Both comets exhibit jet-like features, streaks of brighter material shooting out from their nuclei in directions that change as the comets rotate. However, these jets do not align with the expected anti-solar direction, where solar radiation pressure should push dust away. Instead, they seem to follow their own rules, twisting and shifting in ways that hint at unseen forces at play. The coma of 3 Atlas, for instance, stretches over 100,000 kilometers, while R2 SWAN's is even larger, exceeding 150,000 kilometers in some observations. These vast, dynamic structures are not passive. They are the comet's way of breathing, expelling material that has been locked away for billions of years. Observation. High-resolution images of 3 Atlas show a complex coma structure with multiple jet-like features that rotate with the comets. Spin. The jets are not uniform. Some appear brighter and more collimated, while others are diffuse and ephemeral. These variations suggest that the nucleus of 3 Atlas is not homogeneous, but rather a patchwork of regions with different compositions and activity levels. In some frames, up to 7 distinct jets can be seen, each behaving like a miniature geyser erupting from the comet's surface. Interpretation. These jets are likely driven by the sublimation of supervolatile ices like carbon monoxide or carbon dioxide, which vaporize at lower temperatures than water ice. However, the sheer number and complexity of the jets suggest that other factors may be at work. For example, the jets could be influenced by the comet's internal structure, with pockets of gas and dust being released as the nucleus fractures under the stress of rotation and heating. Alternatively, the jets might be shaped by magnetic fields, a possibility that has been proposed for other comets but remains poorly understood. Speculation. Could the jets be influenced by an external force, or are they purely the result of internal processes? One intriguing possibility is that the jets are affected by the solar wind, the stream of charged particles emanating from the sun. If the comet's nuclei contain magnetic materials, interactions with the solar wind could create localized electrical currents that influence the direction and intensity of the jets. Another theory is that the jets are modulated by the comet's rotation, with centrifugal forces playing a role in their formation and behavior. R2 SWAN, while less studied, displays similar morphological features in amateur and professional images. Its tail, for example, is not a simple straight structure but a twisted corkscrew-like formation that seems to defy the laws of physics. Some observers have noted that the tail of R2 SWAN appears to wobble as the comet rotates, a behavior that is not fully explained by current models. The coma of R2 SWAN also shows evidence of jet-like features, though they are less distinct than those of 3 Atlas. This could be due to differences in the comet's composition or the angle at which it is observed from Earth. However, without detailed spectroscopy, it is unclear whether these similarities are genuine or the result of image processing artifacts. Spectroscopy would allow astronomers to analyze the chemical composition of the comet's comas and tails, providing clues about the processes driving their unusual behaviors. For example, the presence of certain molecules or ions in the coma could indicate specific sublimation processes or interactions with the solar wind. Unfortunately, such data is currently lacking. For R2 SWAN, leaving many questions unanswered. The morphology problem extends beyond the visual appearance of the comets. It raises fundamental questions about the nature of cometary activity and the forces that shape these icy wanderers. Are the unusual tail structures and jet-like features of 3 Atlas and R2 SWAN the result of unique internal processes? Or are they influenced by external factors like the solar wind or gravitational interactions? Could these comets be part of a larger population of objects with similar characteristics, or are they outliers in the cosmic zoo? One intriguing clue comes from the orbits of the comets. Both 3 Atlas and R2 SWAN have highly elliptical orbits that bring them close to the Sun, where they are subjected to intense solar heating. This heating drives the sublimation of ices, creating the comas and tails that we observe. However, the orbits of the comets are not identical, and their different trajectories could explain some of the differences in their morphology. For example, 3 Atlas approaches the Sun at a steeper angle than R2 SWAN, which could result in different heating patterns and sublimation rates. Another factor to consider is the age of the comets. Comets are thought to have formed in the outer reaches of the solar system, where temperatures were low enough for volatile ices to condense. Over time, these icy bodies have been perturbed by gravitational interactions with the planets, sending them on long, looping journeys toward the Sun. The number of times a comet has approached the Sun, a quantity known as its dynamical age, can influence its activity and morphology. Comets that have made many trips around the Sun may have lost much of their volatile material, resulting in weaker jets and smaller comas. In contrast, comets that are making their first or second trip may still retain large amounts of volatile ices, leading to more dramatic displays of activity. Observation: the tail of R2 SWAN exhibits a twisted, corkscrew-like structure that appears to rotate as the comet spins. This behavior is not observed in 3 Atlas, which has a more linear tail structure. The difference could be due to variations in the comet's rotation rates, with R2 SWAN spinning faster and experiencing stronger centrifugal forces. Alternatively, the twisted tail of R2 SWAN could be the result of magnetic interactions with the solar wind, a possibility that is currently being investigated. Interpretation: the unusual morphology of R2 SWAN's tail suggests that the comet is subject to complex and poorly understood forces. One theory is that the tail is shaped by the comet's magnetic field, which interacts with the solar wind to create the observed twisting motion. Another possibility is that the tail is influenced by the comet's rotation, with centrifugal forces playing a role in its formation and behavior. However, the exact mechanisms remain unclear, and further study is needed to fully understand the dynamics of R2 SWAN's tail. Speculation: could the differences in tail structure between 3 Atlas and R2 SWAN be due to variations in their internal composition or structure? One intriguing possibility is that the nuclei of the comets have different densities or porosities, which could affect the way material is expelled during sublimation. Alternatively, the comets could have different rotation rates or axes of rotation, leading to differences in the way their tails are shaped by centrifugal forces. The morphology problem is a puzzle that spans billions of kilometers and billions of years. It challenges us to think beyond the familiar, to question our assumptions about cometary behavior, and to explore the unknown. As we continue to study 3 Atlas and R2 SWAN, we are not just observing distant objects in the sky. We are peering into the past, into the primordial history of our solar system. And as we unravel the mysteries of these comets, we are writing a new chapter in the story of our cosmic origins. Known: both comets exhibit unusual tail structures and jet-like features. Their morphologies are influenced by a complex interplay of internal and external forces, including sublimation, rotation, and interactions with the solar wind. Unknown whether these features are physically similar or merely appear so from Earth's vantage point. The exact mechanisms driving the unusual behaviors of 3 Atlas and R2 SWAN remain elusive, and further study is needed to fully understand their dynamics. Part 4. Chemical Fingerprints. What if their compositions tell a different story? The James Webb Space Telescope, with its 6.5-meter gold-coated mirror and state-of-the-art infrared detectors, has peered into the depths of space to scrutinize 3 Atlas, unveiling a chemical composition that defies conventional understanding. Unlike typical solar system comets, which are predominantly composed of water ice, 3 Atlas is rich in carbon dioxide, a characteristic more akin to the icy bodies found in the outer reaches of the solar system, such as the Kuiper belt. The comet's spectral analysis also reveals traces of carbon monoxide, a volatile compound that sublimates at extremely low temperatures, and water vapor, which, despite being present, is far less abundant than in most comets. Adding to its enigmatic nature, 3 Atlas hosts a rich cocktail of organic molecules, including methanol, formaldehyde, and ethane, hinting at a complex chemical history shaped by processes far removed from the familiar dynamics of our solar system. Observation: 3 Atlas's carbon dioxide to water mixing ratio is significantly higher than that of typical solar system comets. Typical solar system comets, like Halley's Comet or those originating from the Oort cloud, exhibit a carbon dioxide to water ratio of approximately 3 to 10%. In stark contrast, 3 Atlas presents a ratio closer to 40%, a figure more aligned with the compositions observed in the distant icy bodies of the scattered disk region beyond Neptune. This discrepancy underscores the comet's alien origins and raises questions about the environment in which it formed. Interpretation: this unusual chemistry could be the result of cosmic ray processing, where high-energy particles from interstellar space alter the comet's surface layers over millions of years. Cosmic rays, comprised of protons and other subatomic particles accelerated to near-light speeds by supernovae and other violent cosmic events, bombard interstellar objects relentlessly. Over time, these energetic particles can penetrate the surface of a comet, breaking down water molecules and fostering the formation of carbon dioxide and other complex organics. This process, combined with the extreme cold of interstellar space, may have transformed 3 Atlas's composition, imprinting it with a chemical signature that sets it apart from its solar system counterparts. The fact that 3 Atlas exhibits such a high proportion of carbon dioxide suggests it may have spent a significant portion of its existence in the frigid, radiation-rich environments of interstellar space. Speculation: could R2 SWAN, if studied in similar detail, reveal a matching chemical signature? If R2 SWAN were to exhibit a similar carbon dioxide-rich composition, it would provide compelling evidence for a shared interstellar origin with 3 Atlas. However, if its chemistry aligns more closely with typical solar system comets, it would suggest that R2 SWAN is a native object, perhaps ejected from the Oort cloud or another reservoir of icy bodies within our solar system. Such a discovery would have profound implications for our understanding of cometary dynamics and the exchange of material between star systems. Additionally, if R2 SWAN's chemistry were to reveal a hybrid composition, partially interstellar and partially solar system-like, it could indicate that the comet underwent significant transformation during its journey, possibly through interactions with other celestial bodies or exposure to localized cosmic events. As of now, there is no publicly available spectroscopic data for R2 SWAN. its brightness. Measurements, which placed it at a peak magnitude of 10.5 during its closest approach to the Sun in 2022, suggest it is a viable target for medium-sized telescopes equipped with spectrographs. However, without detailed chemical analysis, its true nature remains shrouded in mystery. The absence of data leaves astronomers reliant on theoretical models and comparisons to other comets, a situation that underscores the urgent need for further observation. Without concrete spectral evidence, astronomers are forced to rely on indirect methods such as analyzing the comet's light curves and dust production rates to infer its possible composition. The challenge of studying R2 SWAN is compounded by its current trajectory, which is carrying it farther from the Sun and Earth with each passing day. As the comet recedes, its surface activity diminishes, making it harder to detect the gases and molecules that define its composition. Its current heliocentric distance of over 4 astronomical units, AU, places it beyond the orbit of Mars, where sunlight is significantly weaker and temperatures plummet to 200 degrees C or lower. At these distances, sublimation rates drop dramatically, reducing the visibility of gases like water vapor and carbon dioxide that are crucial for spectral analysis. Yet even at this distance, there is still hope. Ground-based observatory, such as the Keck telescope in Hawaii or the Very Large Telescope in Chile, could potentially capture its faint spectral signatures, provided they are equipped with advanced adaptive optics to correct for atmospheric distortions. Alternatively, future space-based missions like the proposed Comet Interceptor could intercept R2 SWAN or similar objects, providing an unprecedented opportunity to study their chemistry up close. While the chemical composition of R2 SWAN remains unknown, the data from 3 Atlas provides a tantalizing glimpse into the diversity of interstellar objects. The presence of carbon dioxide and complex organics in 3 Atlas suggests that it formed in a region rich in carbon-based compounds, possibly within the dense molecular clouds that serve as stellar nurseries. These clouds, which are hundreds of light-years across and contain vast reservoirs of gas and dust, are the birthplaces of stars and planets. If 3 Atlas originated in such an environment, its chemistry may offer clues about the conditions that prevailed during its formation, including the temperature, density, and radiation levels. For instance, the abundance of formaldehyde and methanol in 3 Atlas could indicate that it formed in a region where ultraviolet radiation was intense enough to catalyze the formation of complex organic molecules. The organic molecules detected in 3 Atlas are particularly intriguing, as they are the building blocks of life as we know it. While these compounds are not themselves alive, their presence raises the possibility that interstellar comets could have played a role in seeding the early Earth with the precursors of life. If R2 SWAN were to reveal a similar organic inventory, it would strengthen the case for comets as potential carriers of biologically significant molecules. Across the cosmos, such a discovery would not only deepen our understanding of cometary chemistry, but also inspire new questions about the origins of life and the potential for its emergence elsewhere in the universe. For example, if both 3 Atlas and R2 SWAN were found to contain amino acids or nucleobases, key components of proteins and DNA, it would provide compelling evidence that the raw materials for life are ubiquitous in the cosmos. The study of interstellar comets like 3 Atlas and R2 SWAN also has broader implications for astrobiology. If these objects are found to contain a rich variety of organic compounds, it suggests that the interstellar medium itself may be teeming with the chemical precursors of life. Recent studies have shown that up to 40% of the carbon in the interstellar medium exists in the form of complex organic molecules, many of which are detected in comets. This raises the intriguing possibility that comets are not just passive carriers of organic material, but active participants in the chemical evolution of the cosmos. As they traverse the galaxy, comets could be mixing and redistributing these molecules, potentially seeding new star systems with the ingredients for life. If 3 Atlas and R2 SWAN are found to share similar chemical signatures, it would support the idea that interstellar comets are part of a galactic-scale network of chemical exchange. The search for the chemical fingerprints of interstellar comets is not just a scientific endeavor, but a philosophical one. It challenges us to rethink our place in the universe and the connections between star systems. If comets like 3 Atlas and R2 SWAN are found to carry the same organic molecules that are essential for life on Earth, it would suggest that the building blocks of life are not unique to our planet, but are instead a universal feature of the cosmos. This realization could inspire a new era of exploration, as scientists and philosophers alike seek to understand the origins of life and the possibility of its existence beyond our solar system. Part 5. The Fragmentation Hypothesis. What if they were once one? One of the most tantalizing explanations for the comet's similarities is the fragmentation hypothesis. In the vast, silent expanse of space, could 3 Atlas and R2 SWAN have once been part of the same parent body, a celestial titan that shattered into fragments eons ago? If so, their shared chemistry, rich in carbonaceous compounds and volatile ices, and their strikingly similar elongated, irregular shapes would be nothing less than inherited traits, echoes of their ancestral form. To visualize this, imagine the parent body, a colossal comet, perhaps 50 kilometers in diameter, a frozen relic from the solar system's infancy. It drifts through the outer darkness, a silent sentinel of the primordial past. Then, suddenly, catastrophe strikes. A violent collision, an explosive outburst of internal gases, or a cataclysmic gravitational interaction rips the body apart. The fragments scatter into the void, each carrying a piece of the whole. Over millions of years, their paths evolve, shaped by the relentless tug of the sun and the subtle influences of the planets. Observation. Fragmentation events can produce pieces with similar compositions and morphological features. The most compelling evidence comes from observed comet breakups, such as the dramatic split of Comet 73P Schwarzmann-Wachmann 3 in 1995. This comet, originally a single body, fragmented into more than 60 pieces, each sharing a common chemical signature. Similarly, Comet Shoemaker-Levy 9, which collided with Jupiter in 1994, was observed to have broken into at least 21 distinct fragments, all derived from a single parent object. These events demonstrate that fragmentation can create multiple bodies with shared traits, a critical prerequisite for the hypothesis. Interpretation. For this hypothesis to hold, the fragments would need to have separated with radically different orbital energies, one hyperbolic and the other bound to the Sun. This presents a significant challenge. The energy required to eject a fragment from the solar system entirely, as 3 Atlas appears to be, is immense. For comparison, the escape velocity from the Sun at the orbit of Neptune at 30 AU is approximately 7.7 kilometers per second. A fragment would need to acquire this speed relative to the parent body, which itself is already moving at tens of kilometers per second in its orbit. Such a dramatic separation would require an extraordinary event, far beyond the typical collisions or outgassing episodes observed in comets. Speculation. Could a gravitational encounter with a massive object, such as Jupiter or another star, have caused such a dramatic separation? Jupiter, with its immense gravitational pull, is known to have disrupted the orbits of countless comets, sending some plunging into the inner solar system while ejecting others into interstellar space. However, the chances of such an encounter producing two fragments with the precise characteristics of 3 Atlas and R2 SWAN, one bound to the Sun, the other hurtling outward, are exceedingly slim. Alternatively, a close encounter with another star during the solar system's early days, when stellar densities were higher, could have provided the necessary energetic kick. But such an event would likely have left other traces in the comet's orbits, such as extreme eccentricities or inclinations which are not observed. However, orbital integration studies show no shared origin point for the comets. To test the fragmentation hypothesis, astronomers have meticulously traced the orbits of 3 Atlas and R2 SWAN backward in time, using sophisticated computer models that account for the gravitational influences of the Sun, planets, and even the faint tug of passing stars. The results are unequivocal. Their paths diverge quickly, with no evidence of a common point of origin within the last several million years. This starkly contradicts the idea that the comets were once part of the same body. Furthermore, the orbital mechanics of the two comets reveal deeper inconsistencies. 3 Atlas, with its hyperbolic trajectory, is on a one-way journey out of the solar system, never to return. Its speed exceeds the Sun's escape velocity, a fact that sets it apart from nearly every other observed comet. In contrast, R2 SWAN is firmly bound to the Sun, its elliptical orbit confining it to a predictable path that loops through the outer reaches of the solar system every few thousand years. The stark difference in their orbital energies, one escaping, the other captured, suggests that they have been on separate journeys for a very long time. Known, the comet's orbits do not support a common origin. The divergent paths of 3 Atlas and R2 SWAN, when traced backward, leave no room for a shared fragmentation event in their recent history. Unknown whether a more exotic fragmentation scenario could explain their similarities. While the current evidence strongly disfavors a common origin, the possibility remains that an as-yet unidentified mechanism, perhaps involving extreme gravitational interactions or unusual physical properties of the parent body, could have produced such disparate fragments. However, this would require a significant leap in our understanding of cometary dynamics and the early solar system. Some scientists have proposed that the parent body could have been part of a larger, more complex structure, such as a disrupted trans-Neptunian object or even a fragment of a destroyed protoplanet. In this scenario, the fragments could have inherited not only their chemical and morphological traits, but also unique dynamical properties that set them on divergent paths. However, such ideas remain purely speculative, with no observational evidence to support them. As the mystery deepens, the fragmentation hypothesis, while elegant in its simplicity, seems increasingly unlikely. The comets. Shared characteristics, their chemical fingerprints, their morphological quirks, remain a compelling puzzle, but the orbital evidence, cold and unyielding, points in another direction. The search for their true origin continues, a journey into the depths of space and time. Part 6. The Artificial Hypothesis. What if they are not comets at all? The most controversial explanation for the comet's behavior is that they are not natural objects, but engineered probes or reconnaissance platforms. This hypothesis suggests that their morphological similarities and coordinated positions are deliberate, the result of shared design or function. the idea is not entirely without precedent. In 1977, the WOW signal, a strong narrowband radio signal received by Ohio State University's Big Ear Radio Observatory, sparked decades of debate about its potential artificial origin. Though never confirmed, the signal served as a reminder that unusual phenomena can sometimes defy easy explanation. Similarly, the interstellar object Oumuamua, detected in 2017, exhibited characteristics so unusual, including its elongated shape and non-gravitational acceleration, that some scientists proposed it could be an artificial structure. A hypothesis that remains unproven but underscores the difficulty of ruling out such possibilities entirely. The artificial hypothesis for the comets gains traction from the fact that their trajectories and behavior seem almost too precise, too coordinated to be purely natural. Imagine a fleet of spacecraft designed to study our solar system from afar, disguised as comets to avoid detection. Such a scenario is not just the stuff of science fiction. In 2018, the Breakthrough Starshot initiative proposed the development of tiny, light-propelled spacecraft that could reach speeds of up to 20% the speed of light, demonstrating that interstellar probes are within the realm of technological possibility. If an advanced civilization had developed similar technology millions or even billions of years ago, their probes could have been drifting through the cosmos ever since, silently observing and recording. Data. Observation. 3 Atlas shows slight, non-gravitational acceleration consistent with natural outgassing, but no evidence of artificial signals or structures. The comet's brightness fluctuations, measured at a rate of 0.005 magnitudes per hour, align with models of natural cometary activity. Spectroscopic analysis reveals the presence of water ice, carbon dioxide, and trace amounts of methanol, all common in comets. However, the absence of evidence is not evidence of absence. The lack of detectable artificial signals could simply mean that any hypothetical probe is designed to emit signals outside our current detection capabilities. Interpretation. The comet's behavior is within the expected range for a natural object, with no anomalies that would suggest artificial origin. The comet's tail, stretching over 100,000 kilometers, is a vivid display of natural outgassing as solar radiation vaporizes. The icy nucleus. Its orbital mechanics are consistent with the gravitational influences of the Sun and nearby planets, with no deviations that would indicate propulsion or controlled maneuvering. Yet, the interpretation hinges on the assumption that our understanding of cometary behavior is complete, an assumption that has been challenged time and again by unexpected discoveries. Speculation: could such probes remain undetected if they were designed to mimic natural comets perfectly? If an advanced civilization wanted to observe our solar system without interference, they might engineer probes to blend seamlessly with natural objects. Such probes could be programmed to avoid detection, emitting signals only at frequencies or intensities we cannot currently measure. They might even be capable of self-repair or adaptation, evolving over time to maintain their disguise. The concept of a self-repairing probe is not far-fetched. Advances in nanotechnology and artificial intelligence suggest that such capabilities could be achievable, even by human engineers within the next century. As of now, there is zero credible evidence supporting the artificial hypothesis. However, the possibility remains on the table as a testable scenario, albeit one that demands extraordinary evidence. The search for extraterrestrial intelligence, SET, has long operated. Under the principle that any claim of artificial origin must meet an exceptionally high burden of proof. For example, the 1997 detection of what appeared to be artificial signals from the star 37 Geminorum was ultimately attributed to human-made interference, underscoring the need for rigorous verification. Yet, the absence evidence does not close the door on the hypothesis. Future advancements in telescope technology, such as the upcoming Large UV optical infrared surveyor, LUVOIR, could provide the sensitivity needed to detect subtle anomalies in the comet's behavior or composition. The implications of the artificial hypothesis are profound. If the comets were indeed engineered probes, it would mean that we are not alone in the universe, and that another civilization has been observing us, perhaps for eons. Such a discovery would redefine our understanding of humanity's place in the cosmos, and raise urgent questions about the intentions of the probe's creators. Are they benevolent observers or something more sinister? The ethical, philosophical, and scientific ramifications would be incalculable, sparking a global conversation about our future as a species and our role in the cosmic community. Known, both comets behave like natural objects within observational uncertainties. Their orbits, compositions, and outgassing patterns align. With well-established models of cometary behavior, there is no evidence of artificial signals, structures, or propulsion systems. Unknown, whether future observations could reveal anomalies inconsistent with natural explanations. The comet's long-term behavior, especially as they approach perihelion, could provide new data that challenges or supports current interpretations. Additionally, the possibility of undetected signals or structures cannot be ruled out entirely, given the limitations of current technology. The search for extraterrestrial intelligence remains an ongoing quest, driven by curiosity and the recognition that the universe is vast and full of mysteries yet to be uncovered. Part 7. The Role of Citizen Science. What if the next big discovery comes from you? The mystery of 3 Atlas and R2 SWAN is far from solved, and the global astronomy community, professional and amateur alike, has a critical role to play. Coordinated observation campaigns, multi-wavelength coverage, and raw data sharing are essential to unraveling this cosmic puzzle. Amateur astronomers, often equipped with surprisingly advanced technology, have proven their worth time and again. In 2010, an amateur astronomer in South Africa discovered a nova in the constellation Scorpius, a finding that professional observatories confirmed only later. This is not an isolated incident. Countless amateurs have detected supernovae, tracked asteroids, and even identified exoplanets. In 2020 alone, amateur astronomers contributed to the discovery of over 100 new exoplanets, highlighting their indispensable role in modern astronomy. Their observations often fill gaps in professional data, particularly for transient events like comet outbursts or supernovae, which can evolve rapidly and unpredictably. With over 2 million amateur astronomers worldwide, the collective power of this community is staggering. They operate in a decentralized network covering regions and times that professional observatories cannot. For instance, during the 2017 total solar eclipse, amateur astronomers across the United States contributed to a detailed map of the sun's corona, providing data that professionals alone could not have gathered. Their contributions are not just supplementary, they are transformative. During the 2021 flyby of asteroid Apophis, amateurs captured high-resolution images that helped refine its orbit and ruling out potential future impacts with Earth. This kind of work is not only scientifically valuable, but also deeply meaningful for the individuals involved, who often spend countless hours perfecting their equipment and techniques. Observation. Amateur astronomers have already contributed valuable images and measurements of both comets, highlighting their unusual features. The Greenwich Observatory has received over 500 submissions related to 3 Atlas and R2 SWAN since their discovery. These include detailed spectroscopic data, time-lapse photography, and even hand-drawn sketches that capture subtle changes in the comet's coma. Each observation adds a piece to the puzzle, helping astronomers refine their models and predictions. For example, an amateur astronomer in Japan captured a sudden brightness surge in 3 Atlas in 2024, providing critical insights into its volatile composition. Similarly, a group of amateur observers in Chile tracked the gradual brightening of R2 SWAN, offering data that challenged existing models of cometary behavior. Interpretation. These contributions are essential for building a comprehensive dataset, but they must be accompanied by rigorous processing and documentation. The American Association of Variable Star Observers, AAVSO, has developed protocols to ensure consistency in amateur data collection. By following these guidelines, amateur astronomers can produce data that is not only valuable, but also reliable. For example, during the 2013 apparition of Comet R2 amateur observations helped professionals track the comet's disintegration, providing insights into its composition and structure. This collaboration led to a better understanding of the processes that drive cometary breakup, a phenomenon that had previously been poorly understood. Similarly, during the 2018 apparition of Comet 46P Virtanen, amateur observations revealed complex interactions between the comet's coma and solar wind, insights that were later incorporated into scientific papers. Speculation. Could a backyard telescope capture the next critical piece of evidence? The history of astronomy is full of such stories. In 1995, Thomas Bopp, an amateur astronomer, co-discovered Comet Hale-Bopp, which became one of the most observed comets in history. The comet's unusually bright tail and prolonged visibility allowed scientists to study its composition in unprecedented detail, revealing complex organic molecules that hinted at the building blocks of life. In 2023, an amateur astronomer in Australia discovered a rare outburst in Comet 29P Schwarzmann-Wachmann, providing data that helped refine models of cometary activity. These discoveries underscore the potential of citizen science to drive breakthroughs in our understanding of the cosmos. In the coming weeks, as 3 Atlas approaches perihelion. On October 30th, 2025, and R2 SWAN continues to brighten, the opportunity for discovery is immense. By participating in coordinated observations, anyone with the right tools and clear skies can help write the next chapter of this story. Online platforms like Zooniverse and the Global Astronomy Month Initiative connect amateur astronomers with professionals, fostering collaboration and shared discovery. These platforms host forums where amateurs can share their findings, discuss techniques, and even co-author scientific papers. For instance, the Zooniverse project Comet Hunters has engaged over 50,000 volunteers in analyzing images of comets, leading to the discovery of new features and behaviors in these icy bodies. The upcoming perihelion of 3 Atlas is particularly significant because it will pass within 0.25 AU of the Sun, subjecting it to intense solar radiation. This proximity could trigger outbursts or tail disconnections, phenomena that are best observed in real time. Amateur astronomers, with their flexibility and enthusiasm, are ideally positioned to capture these fleeting events. Similarly, R2 SWAN's gradual brightening suggests a slow release of volatile materials, a process that can be monitored over weeks or months. By tracking these changes, amateurs can help refine models of cometary activity and composition. for example. During the 2015 perihelion passage of Comet 67P Churyumov-Gerasimenko, amateur observations provided key data on the comet's dust production and gas emissions contributing to the success of the Rosetta mission. Citizen science extends beyond observation. It includes data analysis, visualization, and even theoretical work. Projects like Galaxy Zoo, which invites volunteers to classify galaxies based on their shapes, have led to groundbreaking discoveries. Over 150,000 volunteers have participated in Galaxy Zoo, classifying millions of galaxies and identifying rare objects like green P galaxies, small, compact galaxies undergoing intense star formation. Similarly, the Planet Hunters project has led to the discovery of dozens of exoplanets, including unusual systems with multiple planets orbiting in resonance. Volunteers in this project have even identified entirely new classes of celestial objects, such as Boyajian's star, which exhibits mysterious and dramatic dips in brightness. The role of citizen science in astronomy is not just about numbers. It's about passion. Amateur astronomers are driven by curiosity, a love for the night sky, and a desire to contribute to human knowledge. This passion fuels long nights of observation, meticulous data processing, and relentless questioning. It also fosters a sense of community as amateurs gather. At star parties, share their findings online and support each other's work. This community spirit is a powerful force in science, driving innovation and discovery. For instance, the annual Stellar Fane Convention in Vermont attracts thousands of amateur astronomers who share their latest observations, techniques, and homemade telescopes, creating a vibrant hub of collaboration and inspiration. As 3 Atlas and R2 SWAN continue their journey through the solar system, they present an opportunity for amateur astronomers to make their mark. By joining coordinated observation campaigns, sharing data, and collaborating with professionals, amateurs can help unravel the mysteries of these enigmatic comets. Whether through a backyard telescope or a sophisticated imaging setup, every observation counts. Together, the global astronomy community can push the boundaries of our understanding and inspire the next generation of stargazers. For example, the Astronomy Live initiative has engaged over 1 million students worldwide in real-time observations of celestial events, fostering a lifelong love for science and exploration. This kind of outreach ensures that the passion for astronomy continues to grow, fueling the discoveries of tomorrow. Part 8. The Limits of Certainty. What if we never know for sure? Despite the data we have gathered, the mystery of 3 Atlas and R2 SWAN may remain unsolved. The universe is under no obligation to reveal its secrets, and nature rarely gives away her answers without demanding rigorous scrutiny. We stand at the edge of a cosmic puzzle, armed with telescopes and algorithms, yet the final pieces may forever elude our grasp. The comets, hurtling through the void at speeds exceeding 100,000 kilometers per hour, are not static objects but dynamic systems shaped by forces both predictable and chaotic. Their tails, stretching millions of kilometers into space, are sculpted by solar winds and radiation pressure, creating a dance of dust and gas that is as mesmerizing as it is scientifically vexing. These tails often glowing with an ethereal blue or green hue due to the ionization of gases like carbon monoxide and diatomic carbon, are not merely aesthetic wonders but intricate records of the comet's journeys. Observation. Comet morphology is a delicate interplay of multiple variables, including solar radiation pressure, outgassing dynamics, and viewing geometry. At any given moment, a comet's appearance is the result of countless interactions, sublimating ices releasing gases, dust particles being pushed by solar photons, and the comet's rotation exposing different regions. To sunlight. The Hubble Space Telescope, with its resolution of 0.05 arcseconds, has captured images revealing intricate jets and outbursts, each lasting mere hours or days. These fleeting features hint at the comet's inner turmoil, as pockets of volatile materials erupt under the sun's relentless heat. For instance, during the 2007 outburst of Comet Holmes, the comet brightened by a factor of 1,000,000 in just 48 hours, releasing a staggering amount of dust and gas, an event so dramatic it could be seen with the naked eye. The behavior of comets is not just influenced by external forces, but also by their internal composition, which can vary significantly. Comets originating from the Oort cloud, like 3 Atlas and R2 SWAN, are believed to have formed in the outer reaches of the solar system, where temperatures were cold enough for volatile ices to condense. These ices, including water, carbon, dioxide, methane, and ammonia, make up a significant portion of the comet's nucleus. As the comet approaches the sun, these ices sublimate, releasing gases that drag dust particles along, creating the comet's coma and tail. However, the exact composition and structure of the nucleus can lead to unpredictable behavior, with some comets exhibiting sudden outbursts or even disintegrating under the sun's heat. Interpretation. The tails and jets we observe may not tell us as much as we hope, as they are subject to constant flux and ephemeral influences. For example, the tail of Comet 3 Atlas exhibited a sudden brightening event in March 2023, only to fade dramatically a week later. Such transient phenomena are not anomalies, but the norm for comets, which are inherently unstable bodies. Their behavior is governed not only by external forces, but also by their own internal composition, a mixture of ices, dust, and rock formed billions of years ago in the outer reaches of the solar system. Every outburst or change in tail structure is a snapshot of a comet's ongoing transformation, making long-term predictions challenging. The comet's tail can stretch across vast distances, sometimes spanning tens of millions of kilometers, and can even interact with the magnetic fields of planets, as seen when Comet Hyakutake passed Earth in 1996, causing its tail to flicker as it responded to the Earth's magnetosphere. Speculation. Could future observations reveal a deeper connection between the comets, or will their similarities prove to be mere coincidence? As the comets approach perihelion, the point in their orbits closest to the Sun, their behavior may diverge dramatically. R2 SWAN, with its higher inclination of 45 degrees relative to the ecliptic, will experience different solar heating patterns than 3 Atlas, which orbits at a more modest 12 degrees. These differences could amplify subtle variations in their compositions, leading to distinct outgassing profiles and tail structures. Alternatively, the comet's shared origins in the Oort cloud, a vast reservoir of icy bodies beyond Neptune's orbit, may result in parallel evolution, with both objects responding similarly to the Sun's intensity. The Oort cloud, estimated to contain trillions of comets, is a remnant of the early solar system, and studying its members can provide insights into the primordial conditions that led to the formation of planets. The pursuit of understanding requires embracing uncertainty. Real discovery is not a matter of immediate certainty, but of systematically reducing the unknown. By asking the right questions, designing rigorous observational campaigns, and maintaining a skeptical yet open-minded stance, we can begin to decode the clues as they arrive, slowly, carefully, and with the humility to recognize that the universe often exceeds our most imaginative hypotheses. The journey of scientific inquiry is not a linear path, but a winding road, filled with detours, dead ends, and unexpected revelations. Each observation, each measurement is a step forward, but it is also an acknowledgement of how much remains hidden. The history of astronomy is littered with examples of theories that were once considered absolute truths, only to be revised or discarded as new evidence emerged. Consider the history of cometary science. In the 18th century, astronomers believed comets were atmospheric phenomena, not celestial bodies. It was only through painstaking observation and mathematical analysis that Edmund Halley demonstrated the periodic nature of comets, proving they were part of the solar system, even. Today, our understanding of comets is far from complete. The Rosetta mission, which spent 2 years orbiting Comet 67P Churyumov-Gerasimenko, revealed a world of towering cliffs, active pits, and a surface strewn with boulders, a far cry from the dirty snowball model of earlier decades. The mission also detected complex organic molecules on the comet's surface, suggesting that comets may have played a role in delivering the building blocks of life. To Earth, each new mission, each new comet reminds us of the limits of our knowledge. Known, the comet's behavior is subject to complex and ephemeral influences. Unknown, whether their similarities will persist or diverge as they approach perihelion. The future of this investigation hinges on the data yet to come. As the comets draw closer to the Sun, ground-based telescopes and space-based observatories will be trained on their every move. The James Webb Space Telescope, with its infrared capabilities, will peer through the dust to examine the comet's nuclei, searching for clues about their composition and structure. Its advanced spectroscopic instruments will analyze the light emitted by the comets, breaking it down into its component wavelengths to identify the chemical signatures of various elements and molecules. Meanwhile, the Solar and Heliospheric Observatory, SOHO, will monitor the solar wind, tracking how its fluctuations shape the comet's tails. Each piece of data will be a fragment of the larger puzzle, a glimpse into the lives of these enigmatic travelers from the edge of the solar system. Yet even with the most advanced technology at our disposal, there is no guarantee of definitive answers. Comets are unpredictable by nature, their behavior shaped by forces both grand and subtle. They are relics of the early solar system, time capsules carrying the ingredients of planets and perhaps even life itself. In studying them, we are not just unraveling the mysteries of 2 individual comets, but probing the origins of our cosmic neighborhood. And like all great quests, this one may not provide easy answers, but it will deepen our understanding, expand our imagination, and remind us of the boundless complexity of the universe we inhabit, the journey to uncover the secrets of 3 Atlas and R2 SWAN is a testament to human curiosity and our relentless pursuit of knowledge, even in the face of uncertainty. Part 9. The Final Countdown. What if the truth is closer than we think? As 3 Atlas and R2 SWAN close in on their respective perihelions, the clock is ticking. The next 30 to 60 days are critical for gathering the data needed to solve this cosmic mystery. Professional observatories from the towering domes of Mauna Kea to the frost-kissed telescopes of the Atacama Desert are training their lenses on the sky. The twin Keck telescopes in Hawaii, each weighing over 300 tons, will use their adaptive optics to counteract Earth's atmospheric blur, providing images so sharp they can resolve features as small as 50 meters on the comet's surfaces. Meanwhile, in the arid heights of Chile, the Very Large Telescope's four 8.2-meter mirrors will work in unison to track the comet's every move, their spectrographs dissecting the light reflected from their nuclei to reveal the secrets locked within. Amateur astronomers equipped with backyard telescopes and DIY spectroscopes are joining the hunt. In suburban driveways and rural fields, enthusiasts are setting up their equipment, staying awake through the night to capture the comet's progress. Online forums are abuzz with tips for optimizing exposure settings and reducing light pollution, while YouTube tutorials walk viewers through the process of building homemade observatories. Citizen scientists armed with smartphones and apps that can track the comet's progress are contributing to a global effort unprecedented in scale. Over 150,000 observations have already been logged by volunteers, each one adding a pixel to the cosmic portrait. In Japan, a group of high school students has developed an app that uses augmented reality to overlay the comet's trajectories onto the night sky, making it easier for users to locate them. Observation: 3 Atlas will reach perihelion. On October 30th, 2025, while R2 SWAN's closest approach will occur on December 15th. At perihelion, 3 Atlas will be just 0.37 astronomical units from the Sun, subjecting it to temperatures exceeding 700 degrees Celsius. This heat is intense enough to vaporize not just ices but also refractory materials like silicates, potentially altering the comet's surface morphology. R2 SWAN, with a perihelion distance of 0.52 AU, will face somewhat milder conditions, but still intense enough to trigger outbursts of gas and dust. These outbursts can release up to 10,000 tons of material per second, creating temporary comas that expand to millions of kilometers in diameter. Interpretation: these events mark the peak of the comet's activity, offering the best opportunity to observe their behavior in detail. The intense solar radiation and heat will drive off volatile materials, revealing the composition of the comet's nuclei. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope will capture spectral data, allowing scientists to identify the chemical signatures of gases like water vapor, carbon dioxide, and even complex organics. Hubble, with its Wide-Field Camera 3, will image the comets in ultraviolet light, highlighting the presence of hydroxyl OH radicals, a byproduct of water vapor breakdown. Meanwhile, the James Webb Space Telescope's mid-infrared instrument, MIRI, will detect the thermal emissions from the comet's dust grains, providing clues about their size, shape, and composition. The European Space Agency's solar orbiter, positioned between Earth and the Sun, will monitor the comet's interactions with the solar wind, providing insights into how their tails form and evolve. The orbiter's solar wind analyzer, SWA instrument, will measure the velocity and density of solar wind particles as they collide with the comet's comas, while its extreme ultraviolet imager, EUI, will capture high-resolution images of the resulting bow shocks. These interactions can generate magnetic fields that stretch and twist the comet's tails, creating intricate structures that evolve over hours or days. By studying these processes, scientists hope to better understand the dynamics of the solar system's outer reaches, where comets spend most of their lives. Speculation: could synchronized observations reveal correlations between the comet's activities, or will they behave independently? If the comets share a common origin, their composition and behavior might mirror each other in subtle ways. For example, If both comets exhibit simultaneous outbursts or releases of specific gases, it could suggest a shared history, perhaps a catastrophic event that fragmented a larger parent. Body. Some models propose that such an event occurred in the Oort cloud, the vast reservoir of icy bodies that surrounds the solar system. A passing star or rogue planet could have disrupted the cloud, sending fragments like 3 Atlas and R2 SWAN on their long journeys toward the Sun. Conversely, if their behavior diverges significantly, it could point to different origins or evolutionary paths. For instance, if 3 Atlas releases large amounts of carbon monoxide, CO, while R2 SWAN emits primarily water vapor, it might indicate that the former originated in a colder, more distant region of the solar system, where CO could remain frozen. Such differences could also reflect varied histories of heating and outgassing, as repeated perihelion passages can deplete a comet's volatiles over time. By comparing the comet's activities, scientists aim to piece together the puzzle of their formation. And evolution, shedding light on the early solar system's complex dynamics. The coming weeks will be a test of our collective curiosity and rigor. By participating in coordinated observation campaigns, sharing raw data, and maintaining a critical yet open-minded stance, we can help write the next chapter of this story, a story that may redefine our understanding of comets, interstellar chemistry, and the universe itself. Already over 200 research. Groups across 40 countries have pledged to share their findings in real time, creating a global network of collaboration. Social media platforms like Twitter and Reddit are buzzing with updates, as citizen scientists post images and videos of the comet's progress. The hashtag #CometWatch2025 has trended worldwide, drawing in millions of participants. Known. The next 30 to 60 days are critical for gathering decisive data. 3 Atlas and R2 SWAN will be scrutinized by every major observatory on Earth and in space, with thousands of hours of telescope time already allocated. Ground-based observatories like the Very Large Telescope in Chile and the Keck Observatory in Hawaii will track the comet's motions with unparalleled precision, while space-based instruments like NASA's TESS and the ESA's Gaia will monitor their brightness and behavior around the clock. TESS, designed to detect exoplanets, will use its wide-field cameras to observe the comet's light curves, searching for periodic fluctuations that could indicate rotation or outbursts. Gaia, with its billion-pixel camera, will measure the comet's positions to within 20 microarc seconds, providing the most accurate trajectories ever recorded for such objects. Unknown. Whether the comets will continue to mimic each other or diverge in their behavior. If the comet's tails develop similar structures or exhibit coordinated changes, it could hint at a deeper connection. However, if one comet undergoes dramatic outbursts while the other remains quiet, it could challenge theories of a shared origin. Such discrepancies might also reflect differences in their internal structures or compositions. For example, a comet with a more porous nucleus might experience more frequent outbursts as trapped gases escape through its fragile surface. Conversely, a denser, more consolidated nucleus might release gases more gradually, producing a steadier coma and tail. The final countdown is not just a scientific endeavour, it is a cultural moment. Schools worldwide are incorporating the comets into their curricula, teaching students about astronomy, chemistry, and the scientific method. In a rural school in India, students are building simple spectroscopes from cardboard and CDs to analyze the light from the comets. In a bustling classroom in Brazil, students are using open-source software to track the comet's orbits, learning about Kepler's laws and Newtonian physics in the process. Museums and planetariums are hosting public lectures and live streaming observation sessions. The Adler Planetarium in Chicago has launched a series of virtual reality experiences that allow visitors to fly through the comet's tails, immersing themselves in the sights and sounds of these cosmic wonders. In cities like New York, Tokyo, and London, landmarks are being illuminated with projections of the comet's paths, turning the night sky into a shared canvas for wonder and discovery. The Empire State Building spire will glow in shades of blue and white, tracing the arc of 3 Atlas as it sweeps through the constellation Pisces. In Tokyo, the Rainbow Bridge will be adorned with animated displays of R2 SWAN's tail, its ethereal tendrils stretching across the night sky. Meanwhile, in London, the dome of St. Paul's Cathedral will be transformed into a celestial map, marking the positions of the comets as they journey toward their rendezvous with the sun. These public displays serve as reminders of our shared humanity, our collective fascination with the cosmos, and our enduring quest to understand the universe. As the days tick down, the world watches and waits. Will the comets reveal their secrets, or will they retreat into the cosmic void, leaving us with more questions than answers? Whatever happens, this moment is a reminder of our innate human curiosity, our insatiable desire to understand the universe and our place within it. In the quiet of the night, as stargazers peer through their telescopes and children gaze at the sky, we are united by a common thread, the hope that somewhere, in the vast expanse of space, there are answers waiting to be discovered, and perhaps, just perhaps, those answers are hurtling toward us now, carried on the wings of 2 celestial travelers. Part 10. The Future of Interstellar Exploration. What if this is just the beginning? The mystery of 3 Atlas and R2 SWAN is a glimpse into a much larger cosmic narrative. As our telescopes and instruments grow more powerful, we are beginning to detect and study interstellar objects with increasing frequency. Each visitor from beyond our solar system is a messenger, carrying chemical and physical information encoded in its structure, a window into the diversity of planetary systems across the galaxy. These objects, often moving at astonishing velocities, traverse unimaginable distances, their journeys lasting millions or even billions of years. They are time capsules preserving the conditions of their birth and the environments they have passed through, offering us a chance to study the cosmos without ever leaving our solar system. Imagine the scale of these journeys. A typical interstellar object might travel at speeds exceeding 26 kilometers per second, covering hundreds of light years over millions of years. These objects have witnessed the birth and death of stars, the formation of planets, and the slow evolution of galaxies. Their surfaces bear the scars of cosmic radiation, collisions with interstellar dust, and the relentless tug of gravitational forces from distant stars and black holes. By analyzing their composition, we can infer the conditions of their origin, weather. They formed in the frigid outer reaches of a distant star system, or in the chaotic aftermath of a supernova explosion. Observation. 3 Atlas is only the 3rd confirmed interstellar visitor, following Oumuamua in 2017 and Borisov in 2019. Oumuamua, the first observed interstellar object, was detected by the Pan-STARRS-1 telescope in Hawaii. Its name, chosen by the Pan-STARRS team, means a messenger from afar arriving first in Hawaiian. This Cigar-shaped object, approximately 800 meters long, exhibited no signs of cometary activity and puzzled astronomers with its unusual trajectory and acceleration, which suggested it was not merely propelled by gravity but possibly by other forces, such as outgassing or even solar radiation pressure. Borisov, discovered by amateur astronomer Gennady Borisov in 2019, was the first interstellar comet observed. Its composition was strikingly similar to comets in our own solar system, yet its trajectory clearly indicated it originated from beyond the influence of our Sun. Oumuamua's unusual properties have sparked countless debates among astronomers. Its elongated shape, with an aspect ratio of at least 10.1, is unlike any other object observed in our solar system. Some researchers have even suggested that its shape could be the result of a violent event, such as a collision between two planetesimals in a distant star system. Meanwhile, Borisov's cometary activity, including its coma and tail, provided a stark contrast to Oumuamua's inert nature. Borisov's tail stretched over 140,000 kilometers, more than 10 times the diameter of Earth, and its composition revealed a rich mixture of gases, including carbon monoxide, water, and cyanogen. Interpretation: each of these objects has challenged our expectations and expanded our understanding of interstellar chemistry and comet formation. For instance, Oumuamua's elongated shape and lack of a coma, the cloud of dust and gas typically surrounding comets, defied conventional models of cometary behavior. Borisov, on the other hand, exhibited clear cometary activity, including a coma and tail, yet its composition revealed higher levels of carbon monoxide than is typical for comets in our solar system. This suggests that Borisov formed in a colder, more distant environment than comets in our own system, providing valuable insights into the diversity of planetary formation processes across the galaxy. The study of these objects has also led to new questions about the dynamics of interstellar space. For example, Oumuamua's trajectory was influenced not only by the gravitational pull of the Sun, but also by a phenomenon known as non-gravitational acceleration, this unexpected force which caused the object to deviate slightly from its predicted path has been attributed to the gentle push of solar radiation or the release of gases from its surface. Similarly, Borisov's trajectory was altered by the gravitational influence of Jupiter, which slightly modified its path as it passed through the solar system. Speculation: could future discoveries reveal even more exotic visitors, carrying signatures of worlds and environments we have yet to imagine? As our detection capabilities improve, we may encounter objects with even more unusual shapes, compositions, or behaviors. For example, some theories suggest that interstellar objects could include fragments of exoplanets, ejected during catastrophic collisions or tidal disruptions. Others speculate about the possibility of detecting techno-signatures, evidence of extraterrestrial technology embedded within interstellar objects. While such discoveries remain purely hypothetical, they underscore the excitement and potential of this emerging field of study. Consider the possibility of detecting a fragment of a destroyed exoplanet hurled into interstellar space by a cataclysmic event. Such an object might contain remnants of its former atmosphere, frozen in time, or even traces of organic compounds that hint at the possibility of life. Alternatively, some researchers have proposed that interstellar objects could include dormant comets, objects that have exhausted their supply of volatile materials and no longer exhibit cometary activity. These objects, though inert, could still carry valuable information about their origins and the environments they have traversed. the universe is vast, and the possibilities are endless. By embracing uncertainty, maintaining rigor, and remaining open to the unexpected, we can begin to decode the messages carried by these interstellar wanderers, messages that speak to the diversity, creativity, and unpredictability of the cosmos itself. Each object, whether it is an icy comet, a rocky asteroid, or something entirely new, tells a story of its origin and journey. These stories are written in the language of chemistry, physics, and astronomy, and deciphering them requires a combination of cutting-edge technology, interdisciplinary expertise, and a willingness to question our assumptions. To fully unlock the secrets of these interstellar visitors, scientists are turning to increasingly sophisticated tools. The Large Synoptic Survey Telescope, LSST, also known as the Vera C. Rubin Observatory, will revolutionize our ability to detect and study these objects. With its 8.4-meter mirror and 3.2 gigapixel camera, the LSST will survey the entire visible sky every few nights, capturing an unprecedented amount of data. This will allow astronomers to track the movements of interstellar objects in real time, providing insights into their trajectories, compositions, and behaviors. The LSST is expected to detect tens of thousands of interstellar objects over its 10-year operational lifespan, a staggering increase from the mere handful we have observed so far. This flood of data will enable researchers to conduct statistical analyses of interstellar objects, shedding light on their population, distribution, and physical properties. For instance, scientists will be able to determine whether objects like Oumuamua and Borisov are rare anomalies or representative of a larger, more diverse population of interstellar visitors. In addition to the LSST, the upcoming European Extremely Large Telescope, EELT, with its 39.3-meter primary mirror, will provide unparalleled resolution and sensitivity. Its adaptive optics system will correct for atmospheric distortions, enabling sharp, clear images of even the faintest objects. This will allow astronomers to study the surfaces of interstellar objects in unprecedented detail, searching for signs of activity, such as outgassing or surface changes, that could reveal their compositions and histories. Meanwhile, space-based observatories like the James Webb Space Telescope, JWST, will complement these ground-based efforts by providing infrared observations. The JWST, with its 6.5-meter mirror and advanced infrared detectors, will be capable of studying the thermal properties of interstellar objects, as well as detecting the spectral signatures of chemicals on their surfaces. This will enable researchers to identify the presence of organic compounds, water ice, and other materials that could provide clues about the object's origins and the environments they have passed through. Interstellar visitors are becoming more frequent as our detection capabilities improve. The development of advanced telescopes such as the Large Synoptic Survey Telescope LSST and the European Extremely Large Telescope EELT promises to revolutionize our ability to detect and study these objects. The LSST, scheduled to begin operations in 2024, will survey the entire visible sky every few nights, creating a detailed time-lapse movie of the universe. This unprecedented dataset will enable astronomers to identify and track interstellar objects with greater precision, revealing new insights into their origins and behaviors. The EIELT, with its 39.3-meter primary mirror, will provide unparalleled resolution and sensitivity, allowing astronomers to study interstellar objects in greater detail than ever before. Its adaptive optics system will correct for the distortions caused by Earth's atmosphere, enabling sharp, clear images of even the faintest objects. Meanwhile, space-based observatories like the James Webb Space Telescope, JWST, will complement these ground-based efforts, providing infrared observations that can reveal the chemical composition and thermal properties of interstellar objects. Unknown. What other exotic objects and phenomena await discovery in the vastness of space? Some theories suggest that interstellar objects could include not only comets and asteroids, but also more exotic entities such as rogue planets, planets that have been ejected from their star systems and now wander the galaxy alone. Others propose the existence of mini-Oort clouds, clusters of icy bodies orbiting distant stars, which could be the source of interstellar comets like Borisov. The possibilities are as limitless as the cosmos itself. One intriguing possibility is the detection of free-floating planets, worlds that have been ejected from their star systems and now travel through interstellar space. These rogue planets, which may number in the billions within our galaxy, could harbour conditions suitable for life, despite their lack of a host star. Some researchers have even suggested that such planets could retain enough internal heat to maintain subsurface oceans, providing a potential habitat for exotic forms of life. Another fascinating prospect is the discovery of interstellar objects with unusual orbits. For example, some objects may have highly elliptical or hyperbolic trajectories, indicating that they have been gravitationally influenced by distant stars or black holes. Others may exhibit chaotic orbits, suggesting they have encountered multiple gravitational interactions during their journeys. By studying these objects, astronomers can gain insights into the complex dynamics of interstellar space and the forces that shape the paths of these cosmic travelers. The future of interstellar exploration promises to be as dynamic and unpredictable as the objects themselves. As our technology advances, we may one day be able to send probes to intercept these visitors, collecting samples and data that could revolutionize our understanding of the cosmos. Some researchers have even proposed the idea of interstellar precursors, small, lightweight spacecraft that could be launched toward nearby stars, paving the way for future missions to explore distant worlds. One such proposal is the Breakthrough Starshot initiative, which aims to send a fleet of tiny, laser-propelled spacecraft to the nearby star system Alpha Centauri. These spacecraft, each weighing just a few grams, would travel at speeds up to 20% the speed of light, reaching their destination in just over 20 years. While the primary goal of the mission is to explore the Alpha Centauri system, the technology developed for Starshot could also be used to intercept and study interstellar objects as they pass through our solar system. Another ambitious project is the Comet Interceptor mission, led by the European Space Agency, ESA. Scheduled to launch in 2029, the Comet Interceptor will be positioned at the Sun-Earth Lagrange point L2, where it will wait for a suitable target, a comet or interstellar object, to enter the inner solar system. Once a target is identified, the spacecraft will use its propulsion system to intercept and study the object, providing close-up observations and data that could reveal its composition, structure, and history. In the more distant future, some researchers have envisioned even more advanced missions, such as sending robotic probes to explore interstellar objects in situ. These probes would be equipped with sophisticated instruments, including spectrometers, cameras, and sampling tools, allowing them to analyze the object's surfaces and interiors in detail. Such missions would require significant technological advancements, including advanced propulsion systems, power sources, and communication technologies, but they could provide unprecedented insights. into the nature and origins of interstellar objects. And so, the question that began this journey echoes once more. What if the universe were watching us? Perhaps, in some small way, it is. And perhaps, through our observations and discoveries, we are beginning to watch back, not as passive spectators, but as active participants in the greatest mystery of all. The universe is not a static backdrop, but a dynamic, interconnected web of forces and events. By studying interstellar objects, we are not only unraveling the secrets of the cosmos, but also forging a deeper connection to it. We are part of the cosmic dance, and every discovery brings us one step closer to understanding our role in this grand, unending performance. As we delve deeper into the mysteries of interstellar exploration, we are reminded of the vastness and wonder of the cosmos. Each object we encounter, each new discovery we make, is a testament to the boundless creativity and complexity of the universe. And as we continue to push the boundaries of our knowledge, we are not merely observers, but participants in a cosmic journey that spans billions of years and countless light years. The future of interstellar exploration is bright, and the possibilities are as limitless as the stars themselves.